Hello students, and welcome back to Chemistry A. I'm Ms. Sleight, and today we're going to be talking about orbital diagrams and electron configuration. Now we always need ways to represent the atom so that we can talk about it and try to explain observations of various experiments. So for example, let's say we want to represent a sodium atom. Sodium is going to have 11 electrons that we need to include in our model. So let's start with a quick Bohr model. So we'll start out with our protons and neutrons in the center. Our first energy level can hold 2 electrons. Every energy level after that can hold 8. So we're going to end up with a total of 3 energy levels. So here's our Bohr model. It very nicely shows us protons, neutrons, all of the electrons, and even shows the energy levels that our electrons are in. However, it gives us absolutely no information about orbitals or orbital subshells. If we were to make an accurate wave function representation of all our orbital subshells, we'd get a diagram that kind of looks like this, where we have all of these overlapping shapes going on. Now this is really hard to look at and it's not easy to see how many electrons are there or how many protons. It's just not very useful if we want to be able to easily and quickly identify an element, even though it accurately represents the shapes and arrangements of all the orbitals. What we need is a new representation, one that you can easily tell the number of electrons and what element you're dealing with, while still providing us detailed info on specific orbitals and orbital subshells. That new representation is going to be the orbital diagram. But before we get into exactly how to draw orbital diagrams, we need to talk about some information that your periodic table tells you about orbitals. First off, your periodic table can tell you about the principal quantum number, which we represent with a lowercase n. The principal quantum number represents the relative size and energy level of orbitals, and it's the exact same as the row number for an element on the periodic table. The row number of an element on the periodic table will represent its highest energy level. Additionally, the location of elements on the periodic table can also tell you what subshell is occupied by their outermost electrons. So what I want you to do now is I want you to pull out your periodic table so that we can take a minute to label some of these things on there. So the first thing we're going to do is on the left-hand side of the table, we're going to label principal quantum number for each of our rows. Next, pull out another color because we are going to outline our first 2 columns. This represents the S block. Make sure that you label it as well. Also, helium is still a part of the S block. Get another color. For this section, this is the P block. The middle section here is our D block elements. And don't forget that lanthanum and actinium are also D block elements. And lastly, we have our F block elements. Now let's talk about what our rules for filling our atomic orbitals are. First off is the Aufbau principle, which tells us that electrons will fill the lowest energy level orbitals first, because everything wants to be in a lowest energy state as possible. Hund's rule says that electrons will occupy orbitals singularly before pairing up. And that's because you got to remember electrons are all negative. So if they can spread out and be farther away from each other, that's what they're going to want to do. Third, we have the Pauli exclusion principle. And that says that electrons in the same orbital will have opposite spins. And I'll show you how we're going to represent that in our first example. Now, you are going to want to make some flashcards or something to help you study these 3 terms, because all 3 of these terms will show up as part of a matching section on the test. Let's talk about the specifics of orbital diagrams. In an orbital diagram, the individual orbitals are represented as boxes, and we draw the electrons as arrows. Orbital boxes are grouped together by their subshell, and they are labeled with their energy level and subshell letter. So let's do our first example together. We're going to make an orbital diagram for carbon. Alrighty folks, let's work through this first example. Make sure you have your periodic table handy. The first thing we need to know is how many electrons carbon has, which if we look, carbon has the atomic number 6, so that means it has 6 total electrons. Now, if you look at your periodic table will tell you kind of the order in which orbitals are filled. If you look at our first row, that is represented solely by s orbitals. So the first orbital that you draw is the 1s. And the 1s can hold 2 electrons in it. Now remember, Pauli exclusion principle says that electrons in the same orbital will have opposite spins. So we're going to represent that as one arrow pointing up and a second arrow pointing down. Now if we look at the periodic table, once we get into the second row, the first subshell we hit is s. So our next set of orbitals is the 2s. So I'm going to make a box. I'm going to label it 2s. Again, our s orbitals can hold 2 electrons, one going up, one going down. So far I have 4 total electrons, and I need to have 6 at the end. So let's look and see what the next orbital is. After 2s, we hit the p block in the second row. So our next set of orbitals is the 2p. Remember, a p subshell holds 3 orbitals. So we're going to draw 3 boxes together. So I draw 3 boxes connected together, and I'm going to label it 2p. Now this can hold a maximum of 6 electrons. However, so far I have 2, 4. So I only need to put 2 in here. Now remember, Hund's rule says that our electrons are going to spread out before they pair up. So I'm going to put 1 in this orbital, and I'm going to put the second in a separate orbital so that they're spread out. Now I have all 6 of my electrons represented. So this is the orbital diagram for carbon. Now there's one more thing to remember while we're making orbital diagrams, and that's that some funny things happen with our principal quantum number when we're dealing with D and F block elements. First off, it's that your principal quantum number will actually change. When you move into the D block, the principal quantum number drops by 1. And when you move into the F block, the principal quantum number will drop by 2. And we'll see what that looks like in our second example. Now we're going to take a minute to make an orbital diagram for copper. Now let's look at how D block elements change things. We are doing an orbital diagram for copper now. So if we look at our periodic table, copper is atomic number 29. So that means it's going to have a total of 29 electrons. Well, if you look at your periodic table, first orbital you run across is the 1s. So I'm going to have a box for my 1s orbital, 2 electrons. Once you get to row 2, you hit the 2s and the 2p. So a box for 2s, 2 electrons, and a set of 3 boxes for the 2p. All right, so then we'd go to our third row of the periodic table and you hit the S block, so 3s. And the next thing you hit in the third row is the P block, so 3p. So a box for 3s, 2 electrons in it. 3 boxes together for the 3p. Alrighty. Then when you hit row 4, the first thing you hit is the S block. So we'd make a box for 4s, 2 electrons. Then we hit the D block. All right. Now remember, since even though we're in the 4th row, since in the D block your principal quantum number drops by 1, this isn't going to be 4D. We're going to label it as 3D. And it's going to need 5 boxes all connected together. So 1, 2, 3, 4, 5, and we label it 3D because principal quantum number drops by 1 in the D block. Now we have to figure out how many electrons need to go in our D block. There's 2 ways to do this. First off, let's count how many that we've filled so far. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I'd need to put 9 in here. The other way of figuring this out is looking at the periodic table. If you notice, in the D block, there are 10 columns. If we figure out which numbered column copper is in, you will know how many electrons for copper need to go in the D block. So if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, copper is in the 9th row, or the 9th column of the D block. That corresponds to the 9 electrons it has in its 3D orbital. So I need to make 9 arrows in here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we have a complete orbital diagram for copper. So you can always use your periodic table to figure out what order the orbitals are going to fill in, just like I showed you on the previous examples. Or you can memorize this chart, where following the blue arrows tells you the order in which the orbitals fill. Now, I won't be giving you this chart on the test, so if you want to use it, you'll have to memorize it or know how to write it out on your own when you get the test. So let's do one last example of an orbital diagram together. Let's make an orbital diagram for potassium. So now let me show you how I would use this chart to do our third example. Our third example is potassium, which if we look on our periodic table, potassium has atomic number 19. This means that potassium is going to have 19 electrons. Now, in order to use this chart, I need to know when to stop. So we need to look at what energy level and what subshell potassium is in as well on our periodic table. So if we look here, potassium is in energy level number 4, and it's part of the 4s. So my very last orbital that I should draw is the 4s. That's where I should stop. So according to our chart, my first is the 1s, followed by the 2s, followed by the 2p, After 2p comes 3s. After 3s comes 3p. After 3p comes 4s. So this is my last orbital. So I'm going to count up all my electrons so I know exactly how many electrons need to go in my last orbital. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So that means I need just 1 to get to 19. Now that we've learned how to make orbital diagrams, let's talk about electron configuration. Orbital diagrams are really great because we get a visual of electrons in the orbitals that's still simplified. But sometimes we don't even need that level of detail. Sometimes we can just use a purely symbolic form. And that's what electron configuration is. It's taking orbital diagrams and representing all of their information with just symbols. So for example, our first example that we talked about was carbon. And carbon had an orbital diagram that looked like so. When we go to turn this into electron configuration, you're going to write your label like you normally would, for example, 1s, and then you're going to superscript the number of electrons found, like so. So instead of drawing 2 arrows in a box labeled 1s, we have 1s superscript 2, 2s superscript 2, and 2p superscript 2. So electron configuration, you're going to use the same process as orbital diagrams. It's just a little bit simplified. Let's work through some examples on this. Example number 5, we're going to write the electron configuration for krypton. So we've got krypton, and krypton has 36 electrons. So you can either use the periodic table to figure out the order of the orbitals, or you can use the chart that we showed before. But either way, I need to go until I have 36 electrons, which, if we use our periodic table as a handy helper, krypton is in row 1, 2, 3, 4, and it's a part of the p block. So the 4p orbital should be my last orbital. So I'm going to write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p. Again, there's a couple of ways to do this. You can add up and figure out how many electrons you have so far, or we can look at the periodic table and figure out how many columns in krypton is. So 1, 2, 3, 4, 5, 6. Krypton is in the 6th column of the p block, so there's going to be 6 electrons in its 4p orbital. So we'd write 4p6. Now that we've done krypton, that was a little bit of a long one. I'd like you to try writing the electron configuration for sulfur on your own. Let's see how you did. The electron configuration for sulfur should be 1s2, 2s2, 2p6, 3s2, and 3p4. And that's all that we have for today. Have a great rest of your day.